you to do is follow these steps exactly if you need to run the code. Create a new Jupyter notebook. And for today, we are going to just use an EfficientNet model to fine tune on an already pre-trained model. So over here, we will have image classification. And then the model that we are using is the EfficientNet. Yeah, so we can use EfficientnetB0. Let's try fit EfficientnetB1, which is more better. And then this is what we'll have. For the runtime, we'll need to use a GPU powered runtime. So under connect, click on change runtime type, and then select the T for GPU. And then you can click save. So once you've clicked save, you'll have to click connect. And I'll add a title over here. I'll add a title over here on what we are doing today. So over here, we are going to fit EfficientNet. Then we're going to have B1 for Stanford dogs. So this is the data that we are going to fit with. So if you check the Stanford dogs data, this is what you have. So you can see it's available on Kaggle and it's on classification. So you've got 120 different categories and 20,500 and different 20,500 and different images. So you have the images and their annotations. So we can create a classification model for this. I've connected to a GPU runtime, and you can confirm that this is a GPU runtime by checking the GB space that I have. Since I'll be sharing the code with you in the chat, allow me to type in the code as I'm explaining, and then I'll be giving you 2 minutes for each part for you to set up your notebooks. So the first thing that we will do is we will set up and load our data. So we'll set up and load data. And under setup and data loading, we'll import libraries that we need. We won't be using PyTorch for today. We will use Keras, because Keras is a little bit easier to implement. PyTorch is a little bit complicated, and you'll need time to learn and understand what we are doing over here for you to fully understand this. So we'll have import numpy as np. So this is just for calculations. And then we will have import TensorFlow. We'll have import TensorFlow underscore datasets, yeah, as tfds, and then we'll have import TensorFlow as tf. So that is the first part, and then we will have import matplotlib.pyplot for showing our images once we've gotten them, and then we will have import Keras because we are using the Keras pipeline, and then from Keras we are going to import layers. So from Keras you import layers, and then lastly you'll have from Keras dot applications you import your model. So this is where you import your models. So you'll have EfficientNet, and then you can see you've got the different models of EfficientNet that you could pick. So over here, I'll pick EfficientNetB1, and that's the model that we are going to use. So over here, I'll just add a comment over here because this is something new that you've done. So this is the library. So this is the sample data library. We are not processing any data as of now. So this is the sample data library. And then this is the model library. Okay, I can copy this, I can share it with you in the chat so you can copy that. And then the next thing we need to do is we need to define our image size. So we will have our image size, and the image size is usually determined by the model that you are picking. So image size, we can say image size is determined by EfficientNet model choice. So over here, we will have our image size being equal to 224. We can have a batch size of 32. Let me change mine to 64. And having a batch size of 64 means basically that we are going to run this model a little bit fast. And then on the image sizes, this is what you have to do. So for image sizes, we usually start with 224. So 224, I'll list the image sizes over here starting from 0 to, we have EfficientNet B0 to EfficientNet B7. So we have 224, and then for B1 it's 240 for the image size. For B2 it's 260. For B3 it's 300. And then for B4 it's 380 for image size. For B5 it's 456. And then for B6 is 528. And then for B7 it's 600. So those are the different image sizes that you would have. So from B0 to B7. So we need to change this from 224 to 240. So this is the preset image size for EfficientNet B1. Okay. So this is the expected input size of your images for the model. So you've got that. I'll copy this. I'll share it as well with you in the chat. And then the next thing that I'll do is I'll do the data loading. So over here we will have data loading. Yeah, so for data loading, we will have our dataset underscore name being equal to Stanford dogs. And then we will have our train DS, comma, test DS. And then we've got our DS info. This is the information of the data being equal to tfds dot load. We pass in our dataset name, and then we will have your split on train and test. And then we'll need to add our info, because you can see we've got with info set over here. So we have with info set as true, and then as supervised should be equal to true as well. And then this should load your data set. And then you can create a variable called number of classes. And number of classes is basically there to help you as you are doing your classification task. Because remember, we said that this is a classification task and we are using the EfficientNet B1 model. So we have to specify the number of classes, and this should be equal to ds underscore info, and then we get the features labels, and then we get the number of classes, and then you can run this. I'll copy that code, I'll share it with you in the chat. Then we'll have a 2 minutes break, and then you can just run this to confirm everything is working. If you've got a question on any of these parts, you can ask as the data loading part is running. The dataset is still loading, so let's still give it time for it to fully load. So note, we are not using real world data as of now. I'll share my notebook on real world use case scenario, and then you'll try it out. You'll just use it as reference. but this is basically how you do it for some sample test data. Let's wait for data loading to fully complete and then we can proceed here. So in 2 minutes, it's done. I'll give you 1 more minute and then we can visualize the data. Let's proceed. So the next thing we need to do is we need to resize our images. So the reason as to why we are resizing these images to match these size that we've specified over here, it's because all images that we have usually come in different dimensions. Okay, so we will have our size being equal to, then you'll open brackets and then you'll have your variable image size. You remember we specified that. So we'll have image size for the height and the width. And then we will have our ds underscore train. So this is for our train data set being equal to ds train. And then we map. And then we use a lambda function. So we will have lambda x. So x over here is supposed to represent your image. And then y. So y should be your label, and then you'll have your TensorFlow function, so tf dot image dot resize, and then you're going to resize the image and then add a label to that image as well. So that's what you have. Okay, I can copy this and then replicate it for this part as well. So I've replaced X and Y with image and label for you to know like what we were resizing over there. I'll copy that, I'll share it with you in the chat. And then the next thing we do is we visualize like, so over here we will have a title, sample images, so just for you to see what we have. So these should actually be colored images that you can interact with. So we will have def, and then we will have a format underscore label. We need to format our label, so we will pass in the label, and then over here we are going to have it as a string label, and string label should be equal to label underscore info. So we are getting this from the data dot int to string, so we are converting it to a string, and then we pass in a variable label over here, and then we can return a string label dot split, and then we split on this dash, we extract the first value. So over here it will tell you that label info has not been defined, but it should be okay. So we are going to define label info next. So over here we will have our label info being equal to ds info and then dot features, and then we get the label. So that's where we get label info, and then we can do our visualization. So we will have for I comma, and then in brackets image comma label. So we need to get the image and the label of each image in enumerate, so it's in the form of a dictionary. So we are going to have ds train dot take, we are going to take 9 different samples, so we can have 3 rows and 3 columns. We're going to have x dot, so plt dot subplot 3 by 3, then I plus 1, and then plt dot IamShow. So remember, we usually visualize images using IamShow. We convert our image into a numpy array of type int8, and then we plot, adding title to each and every image that we have. And then we can remove axis. So we will have plt dot axis. It should be off because we don't want to see the axis, we just want to see the images, and then we can run this. So I'll copy this, I'll share it with you, and basically this is what we have. So we've got different dog images over here, and the task of our model will be to take each and every image that we have over here, learn all the different characteristics for the different dogs that exist in the world, and then be able to classify them if you pass that image to your model. So I'll give you 2 minutes to run this. You can experiment with samples as well if you want to, just to see what are the different dog breeds that we have. So 2 minutes, and then we proceed at 8:55. Hope I'm not fast and I'm explaining each and every part clearly. Okay, let's proceed. So I'll teach you now a new concept, and this concept is called data augmentation. So what is data augmentation? So this is something that you usually do when you are training your data. So data augmentation is the process where you increase the number of training samples that you have in your data. So there are different things that you can do. So for example, in our case, we will have our images augmentation, layers being equal to, so we will open square brackets, and then we will add layers dot, we will have a random, we can have random rotation. So we are just rotating the images randomly. So random rotation. And then this random rotation, you have to give it a factor. So over here, we will have a factor of, let's say 15%, so 0.15. Apart from random rotation, we can have layers dot random translation. So you remember these were some of the things that we covered in the theory part. So we've got random translation, you've got random flip, you've got random contrast. So for random translation, you can have a height factor, width factor, You can flip the images randomly, and then you can add random contrast. So these are basically for data augmentation, like increasing the number of images that you'd have. And then we create a function that will apply this. So we will have the image, and then you can have image augmentation. Then you pass in your images. So over here, what you're going to do is you're going to have for layers. So for layer in image underscore augmentation layers, right? That's what you're going to have. You're going to have your images being equal to layer, and then you pass in images. And then what you're going to do is you're going to return the augmented images. So these are the new samples that you have. So this is basically it for data augmentation. Like you are trying to increase the number of image samples that you have, and yeah, you are increasing the number of samples. I'll copy this code, I'll share it with you. And then the next thing we can do is we can visualize this using a sample image. Okay, so over here we've got a sample augmented image. Okay, so for this sample augmented image, we will have for image, comma label. So we will have in ds underscore train dot take one, right? So we will have actually we don't need to do that now. So we'll have for I in range, let's say range 9. So we'll have a 3x3 grid again. We will have our ax being equal to plt dot subplot, and then we will have a 3x3, and then we've got I plus 1, and then we will have our augmented image being equal to this function that we've created over here, image augmentation, and then we will have we can use tf.expand, but I'll switch this to np. We'll use numpy. So np.expand dimensions, and then we've got our image dot numpy, and then let me change this to be correct. Dot numpy, our axis should be equal to 0, and then I can remove these. I don't have to remove that first. We will have our augmented image being equal to, we can use tensorflow.squeeze, but we are using numpy, so we'll have np.array, and then we will have our augmented images. Yeah. So these are for the images that we are creating, and then we will have plt.imshow augmented image 0, and then we don't need to convert it again to an array over here because we've done that up here, and then we visualize it as a int8 object, and then we can add a title, so plt.title, and then for our title, this is what we'll have. So that dot format, then we've got the label for the image, and then we turn off access. So this will visualize our sample image. So I've shared the code with you in the chat. I'll just run this to confirm everything is okay. Yeah, I'll need to run this first, and yeah, it's working just fine. Let's see the visualizations that will be created, and this is what you have. So you can see with augmentation, we've got all these 9 new different samples from a single image. So we've got some sample rotation, we've got flips, and we've got translations, and those are all shown over here. So this is how data augmentation works. So you increase the number of samples that you have just to make your model generalize better. So that should be it for the basic parts. So the next part that we are going to look at will be data preparation for the inputs. Like, how do we prepare the inputs for our model? I'll just give you 3 minutes to have a look at these 2 parts, and then we can proceed. You can actually use this as your template for any task that you will be doing. The only thing that you'll have to add extra over here is data preparation, because you'll need to have your DS train and DS test fully prepared for this. So 3 minutes, you check that, and then we can proceed at 9:05. Okay, it's 9:05. Let's proceed. So the next thing we are going to do, just as I've informed you, is to prepare our data for the model. So if you look at what DS train looks like, so for example, this is DS underscore train. This is what we have. So it's a TensorFlow kind of data set, and everything that we have over there needs to be processed. And the thing that we'll need to do first of all is we will need to one-hot encode or categorical encode values. So this is the first thing that we'll need to do. So we'll have our function over here. So def input and then process underscore train, open brackets. And then what we pass in over here is our image and label. And then our image should be equal to, delete this first of all. So we will have a TF. Yeah, so that is for our label. I forgot the image. So image should be equal to img augmentation. So this is for image augmentation. We can delete this. We don't need to normalize the image. We just leave it as it is. And then label should be equal to tf.1hot encode. And then we label encode the label based off the number of classes that we have. And then we return the image and label. And then for test images, we just need to do this for the label. So we one hot encode the label and number of classes and then return the image and label. And then we apply these functions. So we will have our ds underscore train being equal to ds train dot map, and then we map this to our input process train, and then number of parallel calls should be equal to autotune. So it will automatically choose like how we can preprocess this data. And then you can do the same for DS test. Let's process DS train first fully. So we will have DS train being equal to DS train dot batch, and then we specify the batch size that we have over here, and then drop remainder should be equal to true. So you should drop any values that are left and then just leave the actual values that we have, and then they should be it for train. And then we'll have DS train being equal to DS train prefetch, and then you prefetch this data that has been created for you. We do the same for test dataset. So test should be equal to ds test.map input process test, and then you've got number of parallel should be equal to autotune as well, and then ds test.batch, and then you've got the batch size, and then drop remainder should be equal to true. And then we don't need to prefetch the test dataset. And then yeah, I've shared that code with you, and then we can run this. If there are any errors, it will inform us, so we should be okay up to that point. And then once you've done that, the next thing we do is we train the model from scratch. So over here, it's going to be similar to what we've been doing. Over here, I'll say this is title, and then our model should be equal to, we already loaded the model, so EfficientnetB1 include top should be equal to true. We are including the last layers because I've said that we are fitting this model from scratch, so include top should be equal to true. If we wanted to exclude top layers fine tuning, like if we wanted to phrase some weights, we would say include top should be equal to false, and then weights should be equal to none. Our input size should be equal to the image size that we have over here, and we include the 3 color channels if you remember, and the number of classes we have is the total number of classes that we had initially. Once we've instantiated the model, we compile it, so we'll have model.compile. And then under compiling, if you remember, we usually set our optimizer. So optimizer, we will use the Adam optimizer. We can use keras.optimizer Adam, but in simple terms, we can just type in Adam. And then for loss, we can just type in brackets categorical cross entropy loss. So this is for a multi-class classification task, and that's why we are using categorical cross entropy. Categorical cross entropy should have a underscore there. Let me confirm the spelling. So this should be small c, and then this should be small c as well. And then for our metric over here, we will be monitoring the accuracy of our model. So that's how we compile the model. And then we can get the model summary. So you'll get to see how big the EfficientNet model is, and you'll get to see the architecture of this model as well. So we have that. I'll just run this, and then I'll copy this code. I'll share it with you in the chat. As you are copying that, before you copy that, this is the architecture of the EfficientnetB1 model. You can see it has got lots of layers over here. So it starts with an input layer, and then it goes to a rescaling layer. So this is supposed to rescale your data. And then it has a normalization layer. It has got a stem conv2d pad layer, a stem conv2d layer. So this is a convolutional layer, batch normalization, an activation layer, deepwise conv2d, batch normalization activation, global average pooling. So you can see this is a deep layer that if you were to look at deeply, you will take time, but you can actually look at it and try and understand it. But this is a layer that is actually big compared to the basics that I taught you in class. So you can see like real world models, the ones that are actually being used for applications out here are kind of big as compared to what we look at in class. So these are things that engineers from Google have created to actually make work easy for you. So instead of you creating this whole architecture from scratch, you can just fine tune from what they've created already. So we have that. I'll give you 3 minutes just to have a look at these three sets. And then these two cells, 3 minutes, you have a look at these two cells, and then we can start model training. Okay, let's proceed. So we will now start our model training. So for model training, we have to set the epochs. So, okay, so over here we will have model training. So we need to set the epochs that we run this model for. So we have epochs. You can actually make this as a slider. So I'll just fit this for 5 epochs, just a quick one. And then maybe we can add a slider over here on Colab that you can customize if you want to. So you usually do this by adding at param, right? So you can see it allows you to edit this as an input, and then you can specify the type. Okay, so I'll say the type of item that we'll need over here is a slider, right? So you can see it changes to a slider, so you can customize the epochs if you need to when you are training your models. So maybe we can move it to 11, and then we can specify like the minimum and maximum value. So minimum of 5 and maximum of, let's say, 30 epochs. So that's the maximum that you can train this model for. So let's reduce this to 10. So once we've specified the epochs, we create a variable called history that will store all the values for our model fit. And then we will have model dot fit, open brackets, and then we will have our ds train, and then we specify the epochs, and then we specify the validation data. So this is what we have. I'll copy this, I'll share it with you. And this is basically what we are using to start our model training. So I'll run this. If my GPU allows, like if we've configured the model correctly, then training should start, and we should utilize at least some of the GPU that we have over here without running out of VRAM. So let's wait for epoch 1 to start running, and then we can see if everything is actually okay. But as of now, epoch 1 hasn't started running yet, so model is currently being configured. Let's wait for it to start running. So we will have a look at it, and then I'll comment as we are making progress. So we are fitting this for 10 epochs. You can see over here model is being loaded. So GPU space has jumped from 0 to 4.1 GB. So once the model is fully uploaded to your GPU, training should start. And then these are the parameters that our model has. So these are the total parameters that our model has, and these are the total parameters that we are training, and then untrainable 62. And just as I had said earlier, we can freeze the top, some of the top layers for us to just fine tune a little bit of the weights. So that's what we call pre-training most of the time. But in this class, we are just basically tuning the whole model. And we are training a B1 model, which is relatively small. So let's wait for it to fully on board to the GPU and see if the training starts. Okay. I'll just keep on commenting as the training is proceeding. Yeah, so you can see training has started, and we've jumped from 4 GB to 12.1 gigabytes of GPU VRAM. And this is the first step telling us that it's supposed to take 3 minutes to run. So if you are to run all these 10 epochs, then it would take us 30 minutes to run this whole thing. But let's monitor this for the next 10 minutes and see what will be the validation accuracy and the train accuracy for the first initial fits that we will have done over here. And the reason as to why it's running a little bit slow, it's because we are fitting a relatively big model. So if we would have started with B0, which has a lower number of parameters, that is 4 million, the training will relatively be a little bit more fast. Okay, so first epoch is done running. You can see the accuracy is quite low. So it means the model hasn't figured this thing out yet. So yeah, it basically means that this model won't improve in terms of accuracy that much as we are proceeding on with training, because we've not fully set it up yet, like in a way that will give us the optimum results. So that should be it for today. So for today, it's just showing you like how you can train this model as a whole from scratch. You've seen we've not specified like any CNN models or conv2D layers. We've just prepared our data, we've specified our model, and then we've gone directly to fitting it. So what I'll do is I'll share the last code with you that is for visualizing the history, and then tomorrow we will change this from, so I'll just leave the logs over here so you'll get to see the logs, so that tomorrow we will fine tune this from a pre-trained model, so a model that has already been trained on a larger data set, and see if the accuracy will be different compared to what we have over here. So that should be it for today, but let me just do the final visualization and then we can call it a day. So we will import matplotlib.pyplot as plt, and then over here we will have our function to plot the histories. So we will have def plot history, and then over here we get our hist data, and then we should have a plt dot plot, and then hist dot history, and then we get our accuracy. Then apart from getting accuracy, we can have plt dot plot, and then we can have our validation accuracy. We can skip the loss, we can skip the loss values, but we can have them. Let me remove the loss value, and then we can add our title. So plt dot title, yeah, and then we can have that. So this will plot the accuracies once you are done. So I'd like us to stop there for today because this is going to take time, at least the next 30 minutes to run, but we will begin from here tomorrow. We'll see how we can pre-train a model and how fast will it be compared to just starting from scratch. So that should be it from me for today. I'll stop the class recording.